Why is the sky blue? White light from the sun is made of many different colors, the colors of the rainbow. Red, orange, yellow, green, blue, indigo and violet together make up white light. You might have seen diamonds and crystals sparkle with colors even when the light on them is white. This happens because they separate the white light into the colors it is made of. The air is made of many tiny particles and light can reflect off of them. This is called scattering. These particles can be dust particles or molecules in the gases of the atmosphere. The short answer to why the sky is blue is that the gases in the Earth's atmosphere scatter blue light much more than the other colors. They fill the sky with blue light reflecting and bouncing off the particles in the sky. When we look up to the sky, we see the light coming off the particles, the light that was bouncing on the particles, we see them. But why does blue light scatter? To answer that, we'll need to know what light even is. In the early 1800s, a scientist named Thomas Young ran a simple experiment that proved light was a wave. I did a recreation of his experiment. This is the setup I used. The machine has a laser pointed at two small slits. What do you think I saw on the wall? Two slit-shaped bright spots, right? This is what I saw with just two slits. So how does this prove light's a wave? Here are two waves, the blue one and the red one. The peak of one wave coincides perfectly with the peak of the other wave. The waves are in sync. What would happen if both waves met? There would be a bigger wave with higher peaks and lower troughs. The black wave shows the result. This is called constructive interference. What if we had waves that were out of sync? The troughs of one wave coincide with the peaks of the other wave. The waves would cancel each other out. The peaks are all cancelled out by the troughs of the other wave. The high part of one wave cancels out the low part of the other wave. The black wave is flat because it's the result wave. Destructive interference. Now that we know how waves interfere, we can understand why the double slit experiment proves that light is a wave. Here we can see two water waves interfering. Here we can see that when the two waves interfere, there are alternating places with waves and without waves. If light was a wave, then the two slits from the double slit experiment would make light waves just like the waves the apples are making. The two light waves would interfere and make an alternating pattern with and without waves. The places where there isn't a wave would be dark. There would not be any light there. So if light was a wave, we should see an alternating pattern of bright spots and dark spots from the double slit experiment. This is exactly what we see. And like that, the experiment showed that light is a wave. But there's still a question unanswered. Sound is a wave of air. Water waves are waves in water. If light is a wave, it should be a wave of something, right? To find what light is a wave of, two physicists, Albert Michelson and Edward Morley, conducted an experiment in 1887. They thought that there was a medium that filled the entire universe, called the ether, through which light could move, just like how sound moves through the air. To check if the ether existed, they measured the speed of light in different directions. Because the ether filled the entire universe, they believed that the earth was moving through it as well. If light was traveling in the ether, changing the direction would affect whether the light was moving against the ether or with the ether. Imagine going upstream or downstream in a boat. Same thing. The result? No difference in speed, no matter the direction. What does it mean for light to be a wave then? A field is just a way to attach numbers to each point in space. For electric and magnetic fields, this shows how much electric or magnetic force would be felt at each point and in what direction. The electric and magnetic fields are connected. An oscillating, which means moving back and forth, electric field makes an oscillating magnetic field. An oscillating magnetic field makes an oscillating electric field. Then the oscillating electric field again makes an oscillating magnetic field. This cycle makes a wave in the fields that moves by itself. This was how light was explained. Light is a wave made of oscillating electric fields and oscillating magnetic fields. Let's talk about waves for a second. The height of the wave is also called the amplitude, and the length of one cycle is called the wavelength. This image shows one cycle highlighted in red with the amplitude and wavelength marked. The third aspect of waves is frequency. Frequency is the number of waves that pass each second. Here we see a green wave and a red wave. The green one has more waves passing than the red wave. This means that the green wave has a higher frequency than the red one. For light, changing the frequency or wavelength changes the color of light. Red light has a low frequency and blue light has a high frequency. Increasing the amplitude makes the light brighter. In the atmosphere are many gases. These gases are made of atoms. The atoms have charged electrons. When light from the sun passes near an electron, the oscillating electric fields make the electron oscillate too. The light tugs on the electron and makes it move back and forth. The electron also makes a new electromagnetic wave because charged particles can make oscillating electric fields. We see the new wave as the scattered light. The electron will vibrate at the same rate that the electric field does, and so the color of light scattered will be the same as the color of light that passes near it. What makes the difference, however, is how much the electron vibrates. The more the electron vibrates, the brighter the light. Imagine a swing at a playground. If you try to rock the swing, you might notice that there's a certain rhythm at which it moves the most, where it's the easiest to move at. If I go at exactly that rhythm, the swing goes higher and it moves a lot. If instead I go faster, you can see that I'm pushing against the swing and the swing slows down and it doesn't move much. If I go too slow, then it still doesn't move much. It does not add up and go higher and higher like we saw the first time when I was going at exactly the right rhythm. This shows that this swing is resonant at exactly one rhythm, and at the other rhythms it doesn't move as much. This is like what happens in scattering as well. When the light hits the electron, it starts to vibrate because of the oscillating electric fields. The electron has a frequency at which it will move the most, just like the swing. Nitrogen and oxygen, which make up most of the Earth's atmosphere, resonate in the ultraviolet frequency. Because blue is closer to ultraviolet than other colors, it is scattered the most. And that is the answer to why the sky is blue. Violet is even closer to ultraviolet than blue, but we don't see a violet sky because our eyes don't see violet so well, and the sun doesn't send out a lot of violet light. We can simulate the atmosphere of the Earth using a torch, a tank of water, and some milk. The particles in the milk act like the particles of our atmosphere and scatter the light of the torch. The scattered light is, we see the scattered light as blue and the direct light as yellow. You can see that the light from the torch, the light directly from the torch, has turned yellow. This is because when the light travels through the tank, the blue parts of the light are scattered away. So we see the remaining colors, and when we remove blue from the colors of the rainbow, we get a yellowish glow. When the white light hits the atmosphere, the blue parts are scattered away. The rest of the colors stay mixed together and travel straight. You can see that it looks bluish in my shadow, but then when I move it into the sunlight, it looks yellowish. This is because when the blue parts are gone from the white light, the rest looks yellowish. The direct light from the sun looks yellowish, and the light from the sky looks bluish.